of Mechanical Engineering, Nalla Malla Reddy Engineering College from 22 to 27th September 2025. So before the lecture, I would like to introduce our expert. So today's speaker is Dr. Krishna Kishore. Currently, he is working as an assistant professor in Department of Mechanical Engineering at SVNIT Surat. He has completed his PhD in the area of solid-state welding from NIT Warangal. He has also completed his postdoc at IIT Delhi in the area of wire arc additive manufacturing. He has published more than 30 number of papers in reputed international journals and conferences. His research interests include dissimilar joining, metal additive manufacturing, and clinch bonding. So with this, I request Dr. Krishna Kishore to start his presentation.
Yeah, thank you, Dr. Ajit. Good evening to all of the participants. So today, although I proposed wire additive manufacturing, so today I would like to discuss two different concepts. One is wire additive manufacturing of different alloys, and also I will give some insights on dissimilar joining of aluminum to titanium, which is our core research area. So let me share the PPT. So I will begin with the dissimilar welding, and then I will start discussing on the VAM, which is our topic of your interest. So I hope the screen is visible.
Yes, it is visible.
Yeah, thank you very much. If we see so many industrial applications, if we consider some applications in automotive, let's say the automotive door, right? So we will be not manufacturing the door with one entire material. So we may be using different materials, and these different materials are required to be joined in order to have that structure of door, right? So we may be requiring different properties that are required for designing this entire structure, and we will be tailoring the properties that are required for us from different materials. For example, I may be requiring the application of high temperature, I may be requiring high strength application, I may be requiring for my particular component, I may be requiring wear resistance, I may be requiring corrosion resistance, right? So some material may be having high temperature resistance, some material may be having high corrosion resistance, some material may be having high wear resistance, and some material is very high, having high strength, right? Now, when we tailored these materials, and when we design like this, so then only this complete structure will be having with low weight, low cost, and also reasonable strength and reasonable durability of this particular components, right? So such kind of requirement is there in the industries, and one such application which I would like to discuss is aluminum to titanium joining, right? So the aluminum category is 6061 and titanium category is Ti 64 alloy. So that is the titanium 6 aluminum and 4 vanadium. So what is the need of this joining we will be seeing? So if you see, there is a wide physical and chemical, chemical and mechanical properties variation in both the materials. So one is of low density material, the other one is of high density material. Let's say the density is 2.7, here it is a 4.3, and one is a low strength material, the other one is a high strength material, and also the melting point also varies drastically, and also the other properties like it is susceptible to corrosion, it is having excellent corrosion resistance, like that. Now, if we take the application, so this is the aerospace application. So there is something called as stringer that is attached to the outer body of this like the supporting structure for the aircraft is this kind of skin that is made of aluminum, and there is a stringer that are attached to this one to provide the strength to this particular panel, and these are manufactured with the titanium, right? So wherever this kind of joint is there, this is entirely a dissimilar joint made of aluminum to the titanium, and these are done with different processes. Like we can use fusion welding, like arc welding processes like steel metal arc welding, gas welding, other tungsten welding, other fusion welding like resistance spot welding, beam welding, and other things, and also solid state welding processes like friction stir welding, diffusion bonding, ultrasonic welding, friction roll welding, roll cladding, like that. Right now, we have seen the different properties. Now the differences, if we see, there is a huge difference in the melting point. So when we melt the material, like when we do the melting with the help of fusion welding processes, it will be very difficult. It will be very difficult to join. Even if it is joined during cooling, there might be some kind of crackings that will be occurring. So there will be thermal expansion and contraction, and during service also there might be leading to cracks. And the other one is the formation of the intermetallic compounds when we are melting the fusion with the help of fusion welding. There might be chances of cracking that will be occurring, and also the heating and cooling effects are little bit affecting the microstructure of the grain, also the residual stresses that will be generated during cooling. During the welding, it will be heated, and during the cooling, it will be like dissipating the heat. This will having some kind of residual effect. Also, there will be a potential galvanic corrosion because aluminum is involved, and because of these reasons, the fusion weldings and the fusion welding is generally not recommended for dissimilar joints. And the only promising thing is the solid state welding processes like friction welding, friction stir welding, diffusion bonding, ultrasonic welding, explosive welding, and roll cladding. Now, depending on the shape, depending on the type of the joint we are using, we will be having different processes. Like ultrasonic welding is very suitable for thin structures, and diffusion bonding, it's like suitable. It is having very good surface finish, but we need to have the surfaces to the atomic level, right? We have to have the surface finish to the atomic level, and it will be done with the help of heating and a little application of the pressure. And we have explosive bonding, mostly for the large scale production, and also making the cladded sheets that will be done with the help of this one. Roll cladding is also there. We will be taking two sheets and we will be merging them. We will be attaching just like a glue, and we will be rolling continuously. We will be cutting, rolling. We will be cutting, rolling. All kind of things we will be doing, and this will create a very good surface finish as well as very refined grain structure. So the one which we will be discussing is the friction welding and friction based welding, that is friction stir welding. So friction welding and friction stir welding are little bit similar. Only the thing is here we will be using for the circular components, and we will be creating the relative motion between the workpieces in the friction welding. In the friction stir welding, we will be using a tool that will create the cyclic relative motion. So the first one, just like we will see the video. So these are the two plates to be joined. These are the two plates to be joined. If you can see, this is plate 1, plate 2, and there is third body tool that is coming and inserting into the sheets, just like the video has been shown, and it is continuously rotated. It is continuously rotated. So whenever it is continuously rotated, the particles will also be the tool will also drag the particles, and it will be having the plasticization of the material, right? So here, when we are talking about aluminum to titanium, so mostly the titanium particles will remain like a small fragments, but aluminum alloy, that whatever alloy we are using, 6061, it will be completely plasticized and it will be deformed, and both the materials will try to join. Now, the characteristics of the dissimilar joints. So we will be considering many factors for assessing the joint performance. The joint performance is assessed by the intermetallics. What kind of intermetallics are being formed? So whenever we are talking about aluminum to titanium, so these compounds may be reacting when the welding is happening. So this may lead to some kind of formation of intermetallic compounds, and some thickness of these layers will also be there that we will try to see in the microstructure. Similarly, we may be having the material flow, that is the distribution of titanium, also the distribution of the aluminum on both the sides of the welding. And also we may be having the interface grain structure, some kind of mechanisms will be happening, that is recrystallization and everything, and how much axial force we are applying and what kind of residual stresses that are developing. So all this contribute to the joint performance of my welding, right? So in the friction stir welding, if I want to control any of these factors, I may be controlling these parameters. Maybe the parameters like spindle speed. So it is continuously rotated. The tool is continuously rotated with some RPM and is inserted into the plates to be joining, right? So that is the spindle speed. The second one is the traverse speed. So along the welding line, we will be traveling in order to have the long seam welds. So that is the travel speed. So we may be having the tool offset. We may be having the tool tilt angle. All these parameters contribute to the heat generation and internally to the joint performance. So there are so many gaps that we will be discussing, but the objectives of the current work or the objectives that we will be sharing with you is like this. So it is to understand the process dynamics of friction stir welding process, and also there is a development of tool that we will be discussing, which will be very, very important when we are talking about aluminum to titanium joining, and then to investigate the effectiveness of the developed tool on dissimilar joining of aluminum to titanium. So these are the objectives, and yeah. Now, if you open the machine or if you go to the machine, friction stir weld machine, and if you see, there are different process parameters that we have seen, and there might be some range. There might be some range that is existing. So in the spindle speed, let's say 800 to 1400 is the range we have selected based on the literature survey for this particular category of aluminum to titanium dissimilar joining. And for travel speed might be some 15 to 45, tool offset might be 1 to 3, and tool tilt angle maybe from 1.5 to 2.5. So we have to perform the complete factorial of this all these experiments, and we have to do different iterations in order to find out which parameter is having significant effect, which parameter is not having significant effect. All these things are required in order to optimize, to get an optimized condition, right? So once we do this kind of process dynamics to see the tool impact of tool offset, impact of tool tilt angle, and spindle speed, welding speed, and other things. So we will be fixing the parameters. Let's say here, the spindle speed is fixed to 1200 RPM. The welding speed is fixed to 45. And now the tool offset is getting varied from tool offset for one particular tool offset. We will be varying the different tilt angles and one particular. We will be saying one parameter at once, right? So here, this is the offset. So what is that offset? So here, the titanium is the harder material and the stronger material and high temperature material. The aluminum is the softer material. So since it is softer, so we can plasticize the aluminum more compared to the titanium, and it will also contribute to the tool life. So we will be shifting this axis. We will be shifting this center axis little bit towards the aluminum side. So instead of placing at the center, we will be shifting little bit. So that is the tool offset. So this offset, whatever this offset we are giving, so this offset is towards the aluminum so that the joining will be happening. So if we change the tool offset, let's say only one particular tilt angle we are using, and we will be using the tool offset. This is 1 mm, 2 mm, and 3 mm, right? So you can see there is a variation on 1 mm aluminum side, 1.5 mm aluminum side, 2 mm aluminum side, and 2.5 mm aluminum side. So the more the tool offset we are giving, the more the material is mixing. That is, the more aluminum is getting deformed and it is getting stick to the titanium. So whenever we are completely coming this side, so this is completely plasticized and just sticking like a adhesive bonding. It is not like a chemical bonding. So it is like an adhesive bonding only. It will be sticking. So if there are some fragments of titanium that are mixed, so then there will be a increased titanium mixing into the aluminum side, and there might be some formation of the hooks, right? So increase in the tool offset, there is a material flow increase. Also, if you see at lower offset, there is a less material flow. And with respect to the ultimate tensile strength, so all these parameters we will take, and we will see the ultimate tensile strength at some region. Let's say after some 2.5 or 2, we can say the strength is getting drastically reduced. So that means the contribution of titanium towards this joint strength is becoming less. So that is the reason, even though the material flow is increasing, so there is very less strength observed beyond 2.5 mm offset. So we may fix the offset as 2.5 for the next cases, and we may be doing the variation of the tilt angle, right? So the tilt angle can be varied from 0.5 degree, 1 degree, 2 degree, 3 degree, 2.5 degree, like that. And we can see how well this influence the microstructure. So in the similar way, if you observe the microstructure, if you see the tensile strength, so at 2 degree tilt angle, so previously it is 2.5 for tool offset, we fixed, spindle speed also we fixed, travel speed also we fixed to 45 mm, and now we are fixing the tool tilt angle to the 2 degree. So that is the reason these are the final parameters. 2.5 mm side, 2.5 mm on the aluminum side, tool tilt angle as 2 degree, traverse speed as 45 mm per minute, and spindle speed as 1200 rpm. So these are different criteria for joining the aluminum titanium. So we will be seeing the parameters that are being fixed. This is the experimental setup. So these are some thermocouples nearer to the tool, nearer to the welding zone we have placed in order to monitor the temperature. And these are the tool dimensions, like shoulder diameter is like 18 mm, 12 mm. The shank diameter is 18 mm. Tool pin, it is a tapered one. The top diameter is 6 mm, the bottom diameter is 4 mm, and the tool pin length is 1.6 mm. So the overall, the thickness of the sheet that we are trying to join is 2 mm. And if you take the as received material base structure, so this is for the aluminum and this is for the titanium. So the grain size also you can see some 6.74 micron meter and 3.96 micron meter grain size is there. However, this grain size for this particular aluminum will be mentioning with some aspect ratio. That means the lengthwise this much grain size is there, and the widthwise this much grain size is there. So this is an average for the grains that we are considered for the smaller one. So once we done the welding for the aluminum titanium joining, so we can see this kind of thing. This is the center stitch zone. This is the aluminum side, aluminum interface. This is the titanium side, and this is the titanium interface. And this is the entire material flow after welding we have seen. After welding we have seen this kind of entire material flow. Now if you see on the titanium side, so there are stacking of layers with titanium strips. We can observe these titanium strips will hold the material, so that is creating the gripping in order to have the better joint performance in this case. And if you can also confirm these materials belonging to titanium or not, the EDX scanning will be saying the same thing. So if this green color is showing the presence of titanium percentage 80 to 85%, right? So the other materials also there, like aluminum silicon, which is a part of alloy, aluminum alloy, and the titanium fragments are very much visible, like titanium Ti64, 6 aluminum and 4 vanadium. So the presence of all these elements are quite significant. Similarly, at the middle region, if you see the center steel zone, there are some large fragments of aluminum or large fragments of titanium, and fine particles of this titanium is also existing. And the similar way, if you do the EDX analysis, the similar curve can be seen with a more presence of titanium at the stitch zone as well, and also at the titanium interface zone. And in the aluminum side, if we see, there is a hook structure that is being formed because of the interaction of shoulder driven material and pin driven material. And also this deformed titanium, the titanium particles are deforming here, and some particles will be deformed very heavily, and these will be interacted with the aluminum and will be deposited onto the aluminum side. So this is the interface at aluminum, and if you can see these things in the EBSD, we can clearly distinguish at titanium interface, the grain size is around 1 micron meter. Even at the steel zone also, the grain size is at around 0.9 or approximately 1 micron meter. And each color at this interface is representing the different orientations of the grains related to either aluminum or titanium. So now at interface, what is happening? there is an exothermic reaction that is taking place, that is at the titanium and aluminum interface. So even though the particles are being sheared off in the beginning, but once the plasticity or once the aluminum is completely plasticized and the titanium fragments are trying to mix with the aluminum, so there is a chance of mixing of these aluminum titanium particles, and the plastic during the plasticization there is a exothermic reaction that is taking place. So the exothermic reaction is creating the intermetallics, also the formation of the different compounds that will lead to higher strength on the aluminum or titanium side respectively, that we will try to see with respect to the mechanical properties. So the base material belonging to the titanium, the base material belonging to the aluminum. So, and we can see at the stir zone, that is the center zone of the welding, so there is a drastic change. So these are the related to the titanium side, these are related to the aluminum side, and at the stir zone there is a sudden downfall, right? So whenever we are doing the testing, whenever we are doing the tensile testing or any other hardness testing also, in the dissimilar joining, so there might be some chances like the cracks can be occurring at this zone, right? So our initial thoughts will be to optimize or to reduce this zone, to reduce this variation in the zone. So aluminum or titanium is at somewhere at 300 and the aluminum is somewhere at the 100 hardness, right? So if we can optimize this zone, the chances of failure will be less in the stir zone, right? So otherwise it can, if we reduce this zone, it may be easier to fail at any other different zones like TMAZ or HAZ, depending on the loading type and the crack generation or the weaker zones that are present. Okay. So if we see the tensile test part of this particular material after dissimilar joining, so we can see on the titanium side at the TMAZ, so we can see the strength is the ultimate tensile strength that is achieved is around 270 or 280 megapascal, and around 84.6% is achieved when we compare with the base material of this, with the aluminum side, right? So whenever we are joining aluminum to titanium, the maximum strength that it can achieve is nearer to the weaker material, right? So the stronger material strength we will not be getting when we are continuously applying the tensile testing. So it may break at the maximum UTS of weaker material. So the weaker material here is the aluminum, and we are having an 84% strength compared with the base material, that is the weaker material, aluminum side. And we can further increase this strength by applying some treatments and by designing something. Now our interesting thing that we want to show you is the development of the tool, requirement of the tool, and then different aspects that requirement of the tool we will be discussing, right? So here the major contribution to the joint strength is the heat. So when we are giving more heat, the exothermic reaction between aluminum and titanium is becoming higher, and there is a chance of heavy formation of intermetallics, and these intermetallics, some intermetallics may be contributing to the strength of the material, some may be contributing to the cracking of the material, right? So this is the reason, in order to reduce the heat, so a tool is required, because the heat that is generated is because of the only tool only, right? So because of the interaction of the tool with the workpieces, the heat is getting generated. So here our objective is to develop a tool which is of very low cost, and this tool has to generate very less heat compared to the original one, right? So how we will be doing it? So here the thing is, the friction stir welding tool that we have been used is a continuous tool, and there is a shoulder and pin, and it will be continuously interacting. And what will happen? So the frictional heat is generated at this surface, and also at this surface. Now here, because of the interaction of this much area, the heat generation is more. So if I want to reduce it, I would like to keep the shoulder stationary, and I would like to have the pin only interacting with the materials, right? So for this purpose, if you can see this small video, this is a stationary tool and this is a pin. It will be continuously interacting and it will be doing, right? The shoulder will be stationary and only the pin will be continuously rotating and it will be interacting with the tool, right? So since it is only instead of dynamic action, the shoulder is in dynamic action, only some partial heat will be generated compared to these two. So this is the case where partial heat will be generated, right? The heat generation in this case will be less. So how we will be developing this tool? It will be developed in these three modules, right? In the module 1, there is a pin assembly where pin and holder are there. In the module 2, there is a static shoulder module and different components that we have used for manufacturing this one are been shown. And in the module 3, there is an attachment to the milling machine. So that milling machine requires some holding module. This is the holding module. This is the tool. This is the tool assembly that we have been shown to you, right? So this is the initial drawing and after final manufacturing, this is the assembly, right? So this is the tool assembly that we have designed and this is the application of this one, connecting this entire tool to the vertical milling machine or the friction stir welding machine. And once we attach this one and do the welding, so this is a short video to show how the welding will be done. So here it is continuously rotated. The tool is continuously rotated and the shoulder is kept constant and it will be sliding. It will be just sliding. So because of the sliding only, the heat will be generated. So there will be no other way where the heat will be generated in with the help of the shoulder. So the shoulder is just sliding and because of that reason only the heat is getting generated, right? Now the implementation. So initially this conventional friction stir welding we have seen. Now if we apply the static shoulder friction stir welding, so the only problem we can see here is placing of the tilt angle because the tool is flat. So here the tool tilt angle is restricted to 0 degrees. The tool tilt angle is restricted to the 0 degrees and initially it can be checked whether it is working properly or not. We can check with the aluminum side, right? Only aluminum we are joining, aluminum to aluminum, similar welding. So these are the micrographs we can see for the aluminum side. Since it is aluminum to aluminum, we can see a uniform structure on both advancing side and the retreating side. So this is a base material, original base material. And the previously, if I apply with the only conventional friction stir welding, so these are the microstructures and this is for the static shoulders too, right? So since the heat that is generated is very, very less in the case of stationary tool or static tool, here the grain size that we have formed, the grain size that has been formed is very, very finer. The grain size is very finer and the thermal exposure is less here compared to the conventional tool. So that is the reason the grain has been not grown. And we can see if we can utilize, let's say, the same conventional welding with underwater friction stir welding. So this is the original station. This is the underwater friction stir welding one, and this is the stationary shoulder one. So when we compare even with the a little bit faster cooling rate module, that is the ultrasonic underwater friction stir welding, even then the joints that we are having is very, very less. The joint weld zone that we are having is very, very less, right? So this is the conventional friction stir welding tool. This is underwater and this is the stationary tool, stationary shoulder tool micrograph at the stir region. So we can directly see and compare the microstructure, right? The grain size that has been formed with the help of stationary roller tool, right? So that is only because that we are giving very, very less heat input into the weld zone. And it is only because of the steering action of the pin, the tools pinning action, pinning action of the tool that we have been used, stationary tool. So there is a shearing action at the pin region. And because of this one, because of the sliding of the stationary shoulder tool, the tool will be the material will be mixed and the joining will be taking place, right? And very less zone, very less zone, the material will be squeezed, right? So that is the reason the grain size is very less compared to the underwater, even with the conventional one, and also with the even with the underwater friction stir welding capacities, right? Now, if you see the formation of precipitations or intermetallics or any other compounds that are being there, so it cannot be completely avoided. So some intermetallic compounds, some precipitates are being formed, and these precipitates are very significant when we are doing some kind of cooling treatment. And also we can see this kind of formation of the alpha and beta precipitates in the case of stationary tool also. Right? Now, when we compare the strengths, since the grain size is less, obviously the strengths will be a little bit higher compared to the conventional one. So this is the ultimate tensile strength for the conventional tool, and underwater tool it is 200 some 40, and for stationary tool it is 260 megapascal. So it is like we can say a 70 to 80% again with respect to the parent base material strength. So the weld efficiency is some 80%. So 70 to 85% is the varying, right? With the conventional tool, we are having 70%, and with the stationary tool, we have improved it with little bit 10-15%. So depending on the conditions, it may vary. So 10-15% we have increased the strength, right? So if you see the mechanical aspects, the like micro hardness and other things, so the weld zone will have the lesser strength compared to the base materials, though 100, 10, 100, 80 to 110 is the usual hardness at the for the aluminum side, aluminum, and then the regions, some lower hardness region we can see at the weld zone because of the formation of little bit at the TMAZ and heat affected zone because of this dynamic recrystallization and also the effect of the grain size. So there will be some lesser strength in this region. So some cases we may be seeing the hardness will be higher in the weld zone. Some cases we might be seeing the hardness is heavier in the weld zone. But here in the stationary shoulder tool also, since the interaction of the pin is more compared to the shoulder, so the grain size is forming only in the pin-driven region. Whatever the pin-driven region is there, the grain size formation, formation of fine grains or equiaxed grains is restricted to the pin-driven region only. Now, this has been applied for the similar aluminum to titanium case, the similar way. And this aluminum to titanium also has been implemented in a similar way, like conventional welding, ultrasonic, underwater friction stir welding, and also the stationary shoulder friction stir welding, right? So aluminum to titanium and this kind of configurations, but only in the case of stationary shoulder, we will not be using this kind of tilt angle. So other way, the parameters will be restricted, and because of this tilt angle, little bit less tilt angle, the parameter is little bit increased with respect to the spindle speed, that is 1400 rpm. It is also based on the trial and error experiments only. Okay, so once the welding is been done with the help of stationary shouldered joint, so this kind of interfaces at aluminum side, at titanium side, and at also at the steel zone we can see, and the grain size, how the grain size is varying. So the grain size of the original aluminum that we have been chosen with respect to the aspect ratio is 6.6, let's say 6.7 micron meter, and the titanium is around the 3.96 micron meter, and at the titanium interface it is 2.9 micron meters. Now at the aluminum side, if you see the grain size, it is 6.86 micron meters, because some dynamic recrystallization and other things will be occurring. So there might be some slight increase in the grain size, right? So at the stir zone, we will be seeing, if we see that at the stir zone, so where the center stir zone we will be calling, or we may be calling the pin driven region, the grain size is very finer, that is around 2 micron meter, that is 1.9 micron meter, and the percentage of lower angle grain boundaries, higher angle grain boundaries, and percentage of recrystallization grain boundaries also significantly affecting the strength at the joints, right? Now, this is the entire aluminum to titanium joint. So we can see the base material, heat affected zone, TMAZ, steel zone, again TMAZ, heat affected zone, and base material, right? So at the aluminum side, the base material, these are the parameters. Titanium side, HZ at the aluminum side, HZ at the retreating side, that is advancing side, that is the titanium side, HZ at the retreating side, that is at the aluminum side, and also at the steel zone. Now you see from beginning here to here, there is a complete inhomogeneity in the microstructure, also in the strength parameters, also in the different aspects, right? So there is a need for recrystallization and other things. There is a need for proper cooling of this particular structure. Otherwise, what will happen? So the entire strength is varying, and the different at different zones, different strength is there. At different zones, different strength is there. So although weld is considered as an isotropic only, but still at this different regions, if different strength is there, there will be chances, there might be less prediction that where the crack will be occurring, that we cannot predict it very easily, other than if the heat affected zone or TMAZ or TMAZ are little bit weaker. So that will be the reason. So we need to have at least a homogeneous structure, at least a near homogeneous structure towards this one, right? So we will see what is the reasons for recrystallization at the weldments because of these reactions that is happening. Aluminum to titanium at 600 degrees, 610 degrees centigrade. So this kind of exothermic reaction is happening, and the formation of this recrystallization is being taking place, right? So we can also see this one, the same thing, the same mechanism we can see with respect to this kind of TEM structures, the formation of triple point and the formation of the titanium particles and this kind of ESN structures, right? So when now we see the effectiveness of the tool with respect to the conventional friction stir welding. So there is a lamellar flow, there is a lamellar flow, there is a lamellar flow, even in all the three cases, because of the interaction of the tool with respect to the material, right? So in the stir zone, the size of the stir zone is drastically reduced in the stationary shoulder tool compared to the underwater and the even with the conventional tool, right? Conventional friction stir weld tool. The same tool we have even used with for the underwater welding. So with this also the joint weld region is very low, right? Now, as I said, we have to monitor the temperature in order to understand or in order to control the uniform or near homogeneous structure. So the thermocouples that we have placed at 15 mm, 20 mm, 25 mm. So the maximum temperature that can be recorded, the maximum temperature that can be recorded for different materials can be seen. So for different like different configurations can be seen. That is the for the conventional friction stir weld, underwater friction stir weld, and stationary friction stir weld, right? So for the conventional friction stir weld, it is some around 500 degrees centigrade we can see. Underwater we can see around 450 or something like that. And for the stationary friction stir weld tool, we can see around 380 or like that. Okay. So the heat generation is also very less comparatively comparatively with the help of this one, right? Now, the conventional friction stir weld tool, underwater and stationary. So you can see the strips, right? The size of these particles. These are the titanium strips that are being fragmented from here and being deposited onto the weld region or onto the advancing side. In the underwater welding also, these titanium blocks are there. In the stationary shoulder also, this kind of titanium fragments are being depositing on both advancing side and retreating side, right? So the conventional friction stir weld tool, underwater friction stir weld tool, and the stationary friction stir weld tool. So these are the things, right? Now, if I want to have the uniform microstructure, so only thing is to neutralize this Gibbs free energy we have to calculate, and we have to neutralize for all the cases for ultrasonic like underwater friction stir welding, conventional friction stir welding, and also for the case of this one. Okay, so here just to show one summary table I would like to show here for the case of micro hardness and microstructure. So in order to have this drastic reduction and other things, so some heat treatment techniques might be used in order to reduce this the zone, and the stationary shoulder tool anyway be using the advantage of the low heat and also the fine grains, right? So why I've discussed this dissimilar joining, because when we are talking about metal additive manufacturing, so each layer by layer that we are depositing, each layer by layer depositing. So even though we are depositing the same material, so the layer one behavior with the layer two will be different, right? So starting from layer one to the top layer, the microstructure is completely changing and the complete inhomogeneity is there. Here, because of the interaction of this tool, because of the interaction of the tool from the at the center, at the advancing side, on the, at the retreating side, or at the aluminum side and at the titanium side. So the because of these interactions, because of the chemical reaction, there is a huge formation of grain structures and different variations of the grain structures are there. Okay. So I will just conclude this part, and I will just start the additive manufacturing part. So if you're having any questions related to the uh, welding part or the additive manufacturing part, we can discuss at the end, and then it will be good to summarize both the techniques, and for even this dissimilar case will be there with the help of additive manufacturing, that how it will be there, that we'll be seeing, right? So the other topic, the base topic that I want to discuss is the wire arc additive manufacturing. Here in the wire arc additive manufacturing, although the additive manufacturing is not new technique, so it has been existing since long. And if you see different process steps that we'll be using, so that many people have discussed so far. So from the design state to the final part, that from the designing part to the final part, so there might be so many stages that will be there, like pre-printing, printer pre-processing, simulation, printing, and post-processing in order to see the surface finish and other things, and the final component, right? So there are so many patents that are existing starting from 1980, and the very first technique for the metal has been started at the for the with the help of powder base, that is DED, has been started at 1995, right? So if I show the classification of metal additive manufacturing, so it is a powder bed fusion. There are 7 processes we can say, out of which we can classify like this, like the powder bed fusion with respect to the feedstock, it is a powder, and we may be having a laser based powder bed fusion or an electron beam based powder bed fusion. Similarly, in the direct energy deposition process, so here in the powder bed fusion, we will be depositing layer by layer the powder, and we will be from the top, we will be wherever we are requiring, we will be melting that powder. So here in the direct energy deposition, we are forcing the powder to a we are forcing the powder coaxially onto a laser source, or an electron beam source, or an arc source, or a gas metal source, in order to melt that one and deposit in order to get this component, right? So it is a little bit faster process compared to the powder bed fusion. So in the direct energy deposition also, we may be having laser beam, we may be having electron beam, we may be having plasma arc welding, and we can also use some kind of arc based source. And here the advantages of this DED lies with this one. So the feedstock can be either metallic powder, or it can be of metallic wire. So whatever we will be discussing shortly is related to the metallic wire. And this is a binder jetting machine where we will be using adhesives in order to have this component getting formed, right? So there is a metal powder, and there will be adhesives continuously added each and every layer, and there will be the joining, and this final component will be forming. And this is a sheet lamination where we might be using the same solid state welding processes like ultrasonic welding and friction stir welding also, in order to have this kind of components getting ready, right? So these are the different cases. And in the direct energy deposition, which we are very much interested, so it can be formed on the right hand side. We can see the powders are coaxially forced onto the laser source, so that it will be melted and deposited, and based on the type of the component, we may be either moving the um, DED electrode, or we may be moving the base, that is the platform, in order to have these circular components or any other complex components, right? So instead of using the powder, if we are using a wire, solid metallic wire, and if we are melting with the help of an arc source, then that process is called as wire arc additive manufacturing. So we will be melting that wire with the help of an arc, that is conventional welding processes. Heat source we will be using, like we can use the gas metal arc welding, gas tungsten arc welding, or plasma arc welding, cold metal transfer, like that. And we will be depositing this material in a very faster way, right? So this is a conventional torch we will be using, and this wire, whatever it is coming, so we will be melting and we will be depositing layer by layer. So this instead of welding, we will be depositing, so that, and this entire thing is connected to a CNC controller, so that based on the codes we can easily give the path and everything to deposit. So this is the reason we will be having the continuous depositions and like that, right? So this is a gas metal arc welding, DED process, gas tungsten arc welding, DED process we can use. GTA DED we will be calling, GMA DED, and plasma arc also we can use. So sometimes people will be using the cold metal transfer also, in order to have the better, we can say, the molten pool control, right? So cold metal transfer is one such technique where the spatter losses will be less compared to the this like modified GMAW only, modified gas metal arc welding only. So where we will be having very less uh, very less spatter losses, right? So in the cold metal transfer also, we are having so many techniques, like so many control modes, that is the CMT pulse, CMT dynamic, CMT advanced pulse, and CMT advanced. So what are the these variations, the importance of these variations? So if we see how this is working, so the conventional arc welding, if you remember, we will be maintaining some arc length. We will be maintaining some arc length with respect to the electrode and the workpiece. Let's say that arc length is L, and because of this one, because of ionization and because of we may say the arc column is establishing, right? Because of the gases, shielding gases, because of the thermionic emission, initially the electrons will be getting generated, and these electrons will be excited more by the ionization, and this will be creating this kind of pool of molten metal. And this molten metal here in the cold metal transfer, the arc column, whatever it is getting, so this will be melting the electrode, and we will be giving the oscillation to the electrode, right? Initially, the electrode will come down, it will touch the weld pool. Once it is getting touched, whatever the droplet that is been formed, it will be stick to here. It will be stick because of the adhesion or because of the surface tension forces. It will remain there, and the electrode will be moving backward. The electrode will be moving backward. So the continuous process. So it will, once the electrode is melted, so it will come down, it will touch it, and because of this one, the surface tension forces only, it will be dragged and it will be retreated backside, right? So in this entire process, once the short circuiting is happening, so the droplet detachment is been there, and during that process, the electrode is not given any current supply. So the current will be off for fraction of seconds. So this will be there, so that the whatever the molten droplet that is been generated at the electrode will be transferred to the molten weld pool in a relatively cooler rate compared to the conventional GMAW. So that is the only reason it is given cold metal transfer. Other than that, if we measure the heat, so it will also be having the molten temperature, that is the melting point temperature of the particular material that we are using. Now, if you see different process parameters with respect to different sources and the current challenges in the VAM, right? So with respect to the parameters, if you see, the very one which we'll be using is the heat source. So in the heat source, like if we are going with the conventional GMAW, GTAW, or any other process, we may be having voltage, current, and travel speed. And based on the equipment, that is GMAW, GTAW, or plasma arc welding, and based on the tool path, the type of tool path, right? If you are manufacturing a rectangular one, right? If you are manufacturing a circular one, at what tool path we will be going, right? And depending on the height of the component or depending on the size of the component, how many layers we have to deposit in order to have this microstructure, and the distance between the beads. So if I deposit layer by layer, each layer might be having some width, some thickness. So the distance between the beads, the height of the bead, everything will be calculating. The wire feedstock, that is the composition of the material, the wire material, the diameter of the wire material, and the wire feed rate. The shielding gases also will be using the composition and flow rate. Right? So all these parameters will be mattering a lot in order to have this kind of microstructures, right? For the deposited one, the composition of wire feedstock is very essential in order to have the complete control of the microstructure that are being generated, right? So even the one which we have shown here, so it is having some kind of porosity, some kind of non-uniform in the size of the component, all these things, or some kind of defects we will be seeing, right? Now, the present challenges, if we see, with respect to properties, with respect to the microstructure, with respect to the quality, so there are few challenges, like from bottom to the top of this particular size, bottom to the top of this particular component, if you see, there is a non-homogeneous in the microstructure, like homogeneous structure is not there. So here also you can see there are heavy porosity that is being observed on the top layers. There is fine porosity or less porosity is there. Or for other materials also, if you see, maybe for aluminum the porosity is heavier compared to the steels. The porosity will be 0 for the steels. And if you see, the non-homogeneous in the microstructure will be there, right? The process diversification of the VAM. So if I vary the process like GMAW, GTAW, PA, and CMT, the layers, microstructure, and everything will be varying. And also the improvement of properties is also a limitation. If I want to improve the properties with some conventional techniques, right? So that will be difficult. Heat treatment is anyway possible, but we have to do it for layer by layer, right? So every layer there is a pre-heat treatment required and post-heat treatment required. So that will be becoming challenging. And online detection of the quality, right? So once one layer is deposited, so the layer 1 quality might be different with layer 2, it might be different with layer n, and it might be different with layer n plus 1, right? And also integration of A and in order to have the simulation of this particular process are some challenges that we will be seeing. Okay, so here I just want to show with respect to the first with respect to the stainless steel, then we might be discussing with other alloys like aluminum, ferrous and non-ferrous alloys. We will try to see. Here, this is for particular stainless steel depositant, right? So this is the conventional CMT, conventional mix source, modified mix source we can see, and this is the structure where we will be depositing, right? So you can see there is a thin wall deposited. The wire we have taken is SS316L and the 1.2 mm, right? So there are different parameters like welding speed, voltage, wire feed rate, arc length, total number of layers is 40 here, and varying the parameters, we have deposited different components, right? So although from the top it is looking like it is like welding. So if you see the components like this, so there are some few components that we have deposited, and based on the layer, the total number of layers is 40, and each layer after deposition, each sample after deposition, you can see here from S1 to S9. So at different conditions, different voltages, different current, based on this optimization, like orthogonality, these 9 samples has been manufactured, right? Now, in order to completely understand the inhomogeneity in these particular samples, we may be studying the microstructure, we may be studying the bead analysis, we may be studying the other parameters like tensile strength, hardness, microstructure, everything, right? So we will be extracting the sample in a vertical sample we'll be extracting, and we will be studying the cross section. Let's say these are the 40 layers, and at the junction we will be studying at the bottom of this bottom layers we'll be studying, at the middle layers we'll be studying, and also at the top layers we'll be studying, right? And this is a tensile sample we will be using in order to, this is a micro tensile specimen we can use for doing the tensile testing as per the standards, and the hardness and microstructure has been studied on the same sample, right? Now, this is very important part, right? So if I want to assess the effect of heating, so anyway, the grain size, grain structure or grain size is completely related to the microstructural part only. The microstructural part is the key for the grain size, and it is been completely controlled by the temperature. It has been completely controlled by the temperature, right? So there are two parameters we will be monitoring when we are talking about the welding or when we are talking about the metal arc additive manufacturing or wire arc additive manufacturing in general. So that is the temperature gradient G and also the growth rate R. So that is the solidification rate or growth rate, whatever we will be calling. So at each and every location, we may be calculating the G and also we may be calculating the R depending on the heat and depending on the solidification rate. So these parameters, if we can calculate, we can estimate based on this plot, we can estimate what kind of structure we may be forming and what kind of structure it might be there, right? So there is a wide range of so anyway, generally we will be talking the fine grain structure, the coarse grain structure. So if the growth rate is very low, right, at lower cooling rates, G into R and G by R and G into R are the two ratios we'll be saying. So with respect to G by R ratio, we will be classifying like planar structure, cellular dendritic, columnar dendritic, and equiax dendritic. With respect to the ratio G into R, we may be saying lower cooling rates, higher cooling rates. At lower cooling rates, we may be getting coarser grain structures. At higher cooling rates, we may be getting the finer grain structures, right? So depending on these values, we can easily predict which region it might be there, and we can reconfirm it with the microstructure, right? So now, what is happening in layer by layer? So when we are depositing one first layer and when we are going to deposit in the second layer, what will happen? So the first layer, it is deposited on the substrate, and whatever the heat that is there onto the first layer, it is easily dissipated to the surrounding and also dissipated to the backing plate. It will be dissipated to the backing plate, right? So once it is dissipated to the backing plate, once this heat is dissipated to the backing plate, now the grain structure that has been formed will be little bit, because if the heating plate, the substrate is having high thermal conductivity, it will absorb the heat very faster, right? So depending on that, the grain structure will be dependent, right? The formation of the grain structure will be dependent. Now, if I am depositing another layer, onto the top, right? So this top layer will be depositing heat only to the first layer and to the surrounding, right? So there may be conduction and convection that will be occurring, and radiation is anyway will be there for the during the entire process, right? So partially the radiation will also be there, but mostly the conduction is the major heat dissipation source, and also the convection, because we are continuously supplying the shielding gas along with this arcing. So it will also extract some heat, right? So conduction and convection. The second layer will be depositing the heat or dissipating the heat to the first layer. The third layer will be dissipating the heat to the second layer and first layer. The fifth layer will be depositing the heat to the bottom layers like 1, 2, 3, 4, right? So this process will be continuously there. And depending on the solidification mode of the stainless steel, so from austenite to ferrite or some other combinations, we may be having this kind of phases. So depending on this pseudo binary Bresch diagram, we can say at what temperature this austenitic phase is, fully austenitic phase is there, this rhytic ferrite is there, right? Skeletal ferrite, lathy ferrite, and articular ferrite. So depending on the composition, depending on the temperature at which we will be solidifying, so these kind of structures might be formed, right? Latiferites and skeletal ferrites, right? So this might be there. So now for our samples, if we see for top, middle, and bottom also at the interfaces, you can see a beautiful columnar structures might be there at the very top regions, right? Very top regions, there might be very good columnar structures, because the ratio of this G by R ratio is little bit low compared to the top region, bottom regions, right? So this kind of columnar structures are there. And also if we see the skeletal ferrite, whatever this latiferrite and skeletal delta ferrites are there. So these kind of structures might be observed at the location B, right? And also there is a chance of formation of this base plate. At the base plate, some thickness, there is a diffusion zone, and after that there will be the formation of this finer grains, and also the we can say the formation of dendrite structures, and the growth of dendrites can be seen, right? So this growth is not uniform. This growth is like epitaxial growth is there, and it will be varying. It can randomly form at any direction. It can be randomly formed at any direction. Maybe here you can clearly see. So if I try to zoom it, so here you might be seeing at this region. So it is not necessary like all the dendrites will be forming in the same direction, right? So dendrite may be forming in epitaxial direction. It depends on their basic solidification direction, right? So in which direction it is getting solidified, and it also depends on the formation of the grain orientation and other aspects, right? So these are the aspects that will be covering. These are the aspects that will be governing the grain orientation and the formation of the grain size. So the same thing we will be we also noticed with other samples, the columnar equiaxed grains, and also formation of the coarse grains, latiferrites, and also the skeletal ferrites at some regions, right? So mostly at the top regions we can say there is a formation of columnar structure. At the bottom regions we can say there is a formation of the intersection joint intersection where the base plate and the additive first layer is there. We can say there is a diffuse zone, and there is a formation of dendrites, and also some regions where fine equiaxed grains are there. And at middle and bottom regions, the formation of some equiaxed grains, some coarse grains, and some skeletal ferrite structures, or also some latiferrite structures are also been noticed, right? So now if you see the microstructure of all these different specimens at different conditions of voltage and other thing, although this is the stainless steel of 316L steel, right? And the variation of current is very minimal, 100 to 120 amperes only, and the other parameters are quite not changed, like maybe the shielding gas is restricted to 15 liters per minute. So all these things is contributed to this kind of ultimate tensile strength. The variation is very minimal, which is considered significantly less. But even though it is showing at different regions and different specimens, the region is very less. But within the specimen, so I will not touch up all this analysis with respect to the hardness, or with respect to this Taguchi method and ANOVA. I will just try to show the microstructure and bead height concept. So here, if we see layer by layer and layer by layer microstructure with the help of vision microscope, we can calculate the average bead height, average bead width at each and every layer. What is the bead height and bead width? And as we progress with different specimen, different thickness is there. So this is taken on an average, but as we progress, the thickness is getting reduced. As we progress, the thickness is getting reduced, and it will also be governed by different parameters, right? It will also be governed by different parameters that will actually lead to this one, right? Now this can be controlled by heat treatment process, or also by adding some kind of layer. After one layer depositions, we may be using some other rolling technique, some other preheat treatment techniques in order to control this one, right? Now, for example, for aluminum alloys, if we see at each and every layer, like layer N, interlayer, and the layer N+1, right? So here, the important thing we can see, So this is called as interlayer, and this is called as this between these two layers is called as an interlayer, and this one is called as inner layer, right? So between two layers, whatever the layer is there, that is the inner layer, and the outer one at the interface we can say this is the interlayer. So this is the interlayer and this is the inner layer, right? So each and every inner layer is having some kind of crack, some kind of porosity. So that is a big challenge in aluminum alloys, right? So if I want to avoid this kind of porous structures, if I want to avoid this kind of porous structures, I may be utilizing different what we can say strategies in order to have this kind of strategies in order to do some kind of rolling, right? So this porosity can be controlled by doing some kind of rolling. So one layer we will be depositing, and after that we will be doing this kind of post heat treatment, quality improving treatments like post process treatment, near immersion active cooling, right? So all these techniques we will be doing. So we will be depositing this one entirely into the, and we will be controlling the heat, right? We will be controlling the heat by near immersion. Like we will not be immersing the layer that we are depositing, but whatever already deposited layers are there, we will be trying to immerse this one, right? And also interpass cooling. So once one layer is deposited, we will try to cool with different techniques. Interpass cold rolling. So that means after one layer is deposited, we will be doing the rolling activity, and again this third layer, the other layer will be deposited, and the cooling will be taking place, and so on. So like this, these kind of things are there. Okay. Now, if we see the key benefits of this process, right? The key benefits of this process lies with the manufacturing of large structures. Large structures. When we go with the powder-based techniques, in the powder-based techniques, there is a restriction of the active space or the component space in order to have the deposition within the laser active zone, right? So here we are depositing outside, and just like the arc welding source, we can see. So it can be utilized on the open space, and we can build the big structures, right? So this component is, we are showing the component that bridge Amsterdam 3D printed steel bridge in Amsterdam. It is done with the help of VAM technology, right? So this kind of crane hooks that are being developed with the help of the 3D printed components are being developed with the help of this VAM only. And many cryogenic tanks and many other tanks are being manufactured successfully with the help of this kind of VAM technique, right? So all these challenges, mostly like formation of residual stresses, porosity, cracks, delamination, and other thing. So one such case, one such problem is this kind of staircasing effect. You can see after entire deposition, this is having this kind of structure, right? So this staircasing effect is there. So this can be avoided by proper control of the heat, right? So once we are depositing the first layer, when we are going with the second layer, third layer, fourth layer, fifth layer, each and every individual layers will be having a like variation in the heat, right? So if we attach a vision camera, or if we attach a IR camera to the head where the deposition is happening, and if we are trying to maintain the constant temperature at this deposition layers, right? So if it is the temperature is little bit becoming more or less, we need to adjust process conditions immediately, and we will be depositing, right? So all these things may be reducing the staircasing effect, also the formation of this kind of humping defects, right? So this humping defect is over softening of the material. This whatever this humping or any other things are there. So all these things will be formed because of this overheating or over softening of the material will lead to this kind of defects. So whenever we can see this kind of humping or other activities, we can notice that there is a internal defect or porosity or some kind of cracks are there. Okay. There are so many applications that are there, even with respect to aerospace, marine, and other things. And these are different components that are produced with respect to VAM. Okay. So I think I will stop here with respect to the VAM also. If any queries are there, I will be happy to answer.
Okay, thank you very much, Dr. Krishna sir. You have given very in detail related to welding. So we have talked about in the beginning dissimilar joining of aluminum and titanium.
Yes.
Also, we have talked about wire additive manufacturing. I think our participants now they can ask if any query they are having. Participants, you can directly ask to our speaker, or you can chat your query in the chat box also.
Good evening, sir.
Yeah, good
This
evening.
is Devendra from GBIT.
Yeah, good.
Sir, I want to ask one question, sir,
Yeah.
regarding FSW.
Yes, please.
Sir, what is the most effective method for incorporating nanoparticles into aluminum alloy, sir, to enhance its mechanical properties during friction?
See, one way, generally, whenever people are doing this kind of friction state processing, they will be drilling some holes, right? So they will be drilling some holes, they will be drilling some slots, and on this, they will be inserting some particles, and then they will be doing this processing with the tool. So
Yes, sir.
we have to mainly focus on the pin design. The shoulder interaction will be there. The shoulder will not be actually mixing the particles within the weld region. So the pin design has to be varied in order to understand how the distribution of the particles are there, right? So what people earlier researchers are suggesting, the square pin profile is very good for distribution of particles. So if you can go with a combined square and tapered pin or something, the particle distribution will be very good.
Okay.
So the square pin is very basic research, and if you want to attach, like if you want to add little bit more contribution, you can have the combined pin. So some part may be square, some part may be some kind of tapered pin or like that.
Okay.
So I will just try to show if I'm having one. Let me see. So if there are any other questions, you may ask. Meanwhile, I will try to show one design with you.
Okay, sir.
Participants, if you have any question, you can ask now.
Good evening, sir.
Yeah, good evening.
Yeah, sir. So in metal additive manufacturing, the novel material or uncommon material, just like tantalum or tungsten,
Okay.
having any research scope with respect to the mechanical properties and the process parameter variation.
Yes,
with respect
obviously, people have not published very good number of articles in these materials. But most common applications also we need to see. It is not like the use of the material, new material, but most common applications we can see with respect to titanium, with respect to aluminum and magnesium, right? So the current application that we are having with respect to wire arc additive manufacturing is titanium, right? If you see out of 100 applications, 80 to 90 applications are related to titanium material. So titanium different grades, Inconel different grades, they're been using commonly. So if you can select one application, that will be helpful, because the supporting structure is also very much required. Why you are depositing this material, what is the need of this material and other things. And in the research point of view, obviously we can explore new materials and deposit new materials and study the microstructure, and obviously it will be helpful in publishing.
Okay. And can you use the machine learning approach for predicting
Yes,
mechanical?
obviously machine learning approach can be used.
Okay. Yes. Okay. Thank you.
So related to the previous question, I think the screen is visible now.
Yes, sir. Yes, sir.
Yeah. So here the conventional tools what people are using, so that can also be used, and you can also vary this kind of pins. Okay, right? So here you can see there is a combination of triangular pin at the end, and also there is a tapered pin, right? The triangular pin and taper pin can be combined, the triangles, taper, triangle, taper, depending on your requirement of distribution of particles on both advancing side and retreating side, right? So these different combinations of pins are there, right? So the profiles that you can vary with respect to the end surface. Simple circular, smooth, triangular, tri-fluted structures, three-sided, four-sided, and also the variation of different pins, right? So people have published n number of articles related to this pin geometry, shoulder geometry, and other things, right? So you may select one such profile which is been already been claimed as a very best profile as a beginner, and then after 1 to X months you may be modifying the uh, pin profiles in order to have a better distribution of particles, right?
Okay.
So if there are any queries, obviously you can also reach to me. I'm just dropping my email ID here.
Yes. So participants, if you have any query, you can directly mail to Dr. Krishna Kishore, or you can contact him. So with this, thank you once again, Dr. Krishna Kishore, for your valuable time and delivering such a wonderful and insightful session on welding. So on behalf of our organizing committee and from all participants, so we extend our sincere gratitude for sharing your expertise, and also we are expecting more lectures in the future. So thank you once again.
Thank you, sir. Thank you once again for inviting me, and thanks to all the participants for patiently listening to me. Thank you very much, and see you all. Bye bye.
Bye. So may